now we talk about architecture and about composition. In a way, I can say what I tell you now has almost nothing to do with Petri nets, but which is a very general principle of composition. And I'm sure in the future, composition will be done according to these guidelines. And why this is a good belief, and I'm sure you will believe this also after a while, that I will show you now. So let's turn to what is classical theoretical informatics. What do they do? They start with an alphabet, for instance, alpha, beta, gamma. That is a set of 3 symbols, and that is called an alphabet. And I'm sure everybody understood what I mean, and even Frank understood, despite the fact that he came late, which I do not appreciate that he came late. Okay, so an alphabet. Now comes the, say, theoretical computer science machinery. If you have a fixed alphabet, then you know what a word over the alphabet is, for instance, beta, gamma, or beta, alpha, alpha. These are words over the alphabet. When you know what a word is, then you know what the set of all words is. It is usually called lambda star. Then you know what composition of words is, very important. For instance, if you compose those 3 words, then this will come out. And what is important is that the order in which you do this is not important. So when you compose first those 2, and then before that this one, it is the same as if you first compose those 2 and then this one. This is so trivial that one almost never talks about this, because you cannot imagine that it is not the case. But this is absolutely fundamental, of course, that you don't have to make brackets. Okay? It is called associativity. But I don't want to do much burden on your brain. Okay. So now we can say the set of all words and this composition operator and the NP word, which we call epsilon, is what the mathematicians call a monoid. That is the algebraic term of this. Has anybody a problem with this approach? No. That is good, because composition in the sense that I show you now is not more than that. Now we start in Heraklion. You have an alphabet, like you have here. And you have canonical constructs. The first is you have modules. Now you don't have words, but you have modules. And then you remember a module has an interface. Interface is a set of gates, and each gate has a label, and the labels are in the alphabet. Okay? So when you know what an alphabet is, or when the alphabet is given, then the set of all modules is given. Modules is given. Okay? Because inside the module there can be whatever you wish. And then you have the set of all modules. You write it this way, lambda n, depending on the fixed alphabet. Then we have a composition of modules, and now this fantastic. And the composition of modules is a monoid. Composition will be associative, and we have an empty module, and this is the formal basis of modeling. Okay. So whenever you will in the future make modules and compose something, do it this way. Everything else is stupid. Now, what is a module? So far we only know a module has an interface which has labeled gates, but we don't know what, in the most abstract sense, a module is. Well, a module is something like a graph. Any graph structure can be a module. We have a graph with nodes A, B, C, D, F, and now we equip the module with we take 2 subsets of the nodes, the left one and the right one, and we call the elements gates, and that is already almost a module. Now we do the following. Each gate has got a label. Okay, and in this very simple example, we have even got all labels alike. There is only one kind of labels, all got the label A, alpha. So, from this alphabet, remember. Okay, this is a model. Anybody a problem? Now we have a second module that has the nodes G, K, H, I, G, and they also have labels, and almost everybody has also labeled alpha, but this one has labeled beta. Okay? Please.
And it's a directed graph.
Directed under, it is completely irrelevant. It is a graph structure. If you prefer directed, do it. If it's undirected,
so the gates are all the same. It's not input gate, output gate. It's all the same. They are just gates.
They are just gates. A gate is a node, and a node has a label, and the gate has a label. Nothing else. There may be an arc going to the gate and from the gate within one model. Okay.
And I think the important is that you have left and right interfaces.
This
right?
is the important point. The interface is split into left and right. This is absolutely crucial. Okay. So we have a second model, and now we want to compose them. And I've told already what composition means. So the right interface of the left module is glued with the left interface of the right module. So we consider only those stuff. So this A and this K has nothing to do with each other. Now, we compose D with G, and you see this here, it becomes an internal node of the composed system. We compose E with H, it's also an internal system node, and the F has no partner. So the F goes to the right interface of the composed system.
What if I combine D and H instead of D and G?
This is why I give the example to have this. So I say D goes with G, and I say D does not go with H. So, of course, you say, what shows me that this is the intention? Because composition should be deterministic. This is the result, nothing else. But this is the case because equally labeled gates are ordered. So D is, in this interface here, D is the first element, which is labeled A, D is the second element that is labeled A, and F is the third element that is labeled A. Okay. So in this interface here, G is the first element that is labeled A, H is the second that is labeled A, I has a beta, it is not ordered. And now you compose, or you merge equally labeled and equal and with the same index.
So what is alpha and beta? What is it?
Alpha and beta are labels.
Are labels.
From the given, remember I started with the alphabet.
Yeah, okay.
So you say that now the left interface nodes are ordered, and also the right interface lefts are ordered. So there's an internal order. There's the first and the second and the third interface on the right side.
And the elements, the gates are ordered.
Yes.
Yes, and only equally labeled gates are ordered. For instance, F is not ordered at all. There is no need to order. Only when they're equally labeled, they are ordered. And to merge, you merge elements with the same label and in the right order.
And you do assume that the modeler defines the ordering.
Yes, of course, yeah.
Did you invent some guidelines how to determine the order? Because it seems to be important.
No, because on this abstract level you don't have this kind of guidelines.
You want to convince us to use it.
Yeah. When you later on make a concrete instantiation of this, for instance, patronets of it, people, and then on this level we should make guidelines like this. Here we just say we draw them on the interface in the right order, because we don't want to tell the order. So
the
this,
gate cannot be both left and right. It has to be either left or right.
that is a good question. So far I showed you interface in the gate is either left or right. I'll tell you the story in a minute.
Okay, thank you.
So the point is, if you do it this way, and if you define the composition this way, then the result is always associative. This kind of composition is associative. And that is the crucial point, because whenever you even change a little bit this definition, it is no longer associative. Okay? So it took me a while to prove that. And then when I finished the proof, and now I come to your question, when I finished the proof, I realized I never assumed in the proof that that the gate is either left or right. So it could be left and right. And I was really surprised that this works out. And then I thought,
Composition
okay,
can lead to recursion.
yeah, in a way. But then first I thought, okay, it is not necessary that they are disjoint, that left and right is disjoint, but we never can use it. And after a while, I found a lot of applications where this is very useful. Okay? So it is not necessary that left and right are disjoint, but I don't want to show you examples. But it is fantastic how you can.
Yeah, but then I'm confused again. If you don't distinguish between left and right, how does the matchmaking happen? And then for
assume D is also on the
Yeah.
in this.
Yeah.
So then you compose them, and then D remains on the left side.
But how do you show it in the box? Then you have two instances of the same gate, so to speak, inside the box.
Then you have a graphical problem.
Yeah, exactly.
Yeah,
Yes,
Exactly.
yes, I agree with this. And slowly you get graphical problem, but not mathematical problem. And we have some tricks, so to speak, or some means how to do it graphically. But it's a graphical problem and not a conceptual problem. Okay? So as I said, this definition. Yeah.
Think about the Möbius ribbon. We discussed it over lunch.
Wormholes.
I think these are wonderful examples, but only after 2 bottles of wine I will start thinking
Tonight, tonight, okay.
about Möbius or something. Yeah. Okay, so my point is, this is the general way to compose whatever you have. And do it this way, and as I said, change a little bit the definition and you get punished because any change is not associative. This one is, yeah.
I'm almost afraid to ask this question. I really don't. Okay. No, I'm just honestly interested. This is just from the point of view of interest. Whether you ever look at categorical concepts to formalize this in that world. I'm just thinking because of the monoidal basic structure. I'm not trying to say that you should or that it would be a benefit maybe, but it just interested me to know if you ever thought in that direction.
I thought about half an hour in this direction.
Okay.
I'm not very familiar with category theory, and then I thought I will surely meet in my future life somebody who is much smarter in category theory, and he will tell me this is just a push out of whatever.
I don't know if that would be sort of the answer. And that's also not the direction of, I mean, I would find it kind of interesting actually to ask the question and answer it. And I would not expect that it would be something like, oh yeah, this is just that, this, that. Because I think there are some things, I mean, there are a couple of things that go beyond the monoid here. I mean, in order to get these pictures right, there are a few extra things that need to go in there, but I thought it would be interesting if it turned out that there would be a natural categorical basis for this, that I would just, I mean, if it were me, I would think it would be a nice thing to know.
I did a little bit different. I asked some mathematicians on algebra mathematicians if they have ever seen this kind of structure in algebra. And the typical answer is, look, every 2 weeks there comes a big volume of new algebras. And maybe in some 3 years, maybe 3 years ago, somebody has done it in some journal, but you will never find it. So this kind of algebras, they produce algebras, but they have no classification, and then you never find this. So it may be the case that just for fun somebody invented this, but certainly had not this application. So we have a real application here. Okay, so what is also interesting here, if this happens, if the two given modules are petrinets and you compose them, the result is a petrinet. If they are finite state automata and you compose them, it's not a finite state automata, because suddenly it has two controls. Okay? And there you see how stupid distributed finite automata worlds are. There are many attempts, and then you make Cartesian product, all this wrong stuff. Here you get it very naturally. Unfortunately, it's again a petrinet. In the interface, maybe place, maybe transitions, it makes really no problem. Okay, now I have to go there. We can click this. Ah, yeah, this was it. Peter.
Was before? We skipped over a slide. Yeah. You didn't tell us about this one.
But here I've written the date may lie on the left as well as the right.
Okay. Then we come back to the dynamics. And here I'd like to start with an example to show you the main concepts and ideas for describing the dynamics perspective. Think about a van. This might be a picture of the fan in your hotel room. And typically, if you try to describe the behavior of such a fan, you might have some text. Don't want to read you the complete text, but I like to show you what is the main idea, how to convert and how to identify the dynamic behavior of this van. And what is typically for texts in English or other languages, that you have different states and different transitions. Here, for example, the fan is off. Is one typical state, or another one is the fan is on. Of course, there is an event, turn on the fan, or the fan will start, turn off the fan, turn off the light, sorry. Turn off, turn on. These are typically events and typically states which might happen in such an application domain. And if you have some text, you can mark the events, mark the states. What is then possible that you use this information to describe, to identify some elementary steps in the application domain. And in this example, you see you have 4 different steps: turn light on, fan starts, turn light off, and fan stops. And if you look at the color coding, you see that many of these states and many of these events can be extracted from the text. So the interesting question, of course, is what is the source of the text? Maybe you have a description of that, maybe you can do some interviews with different users in the application domain, and by doing that you have some elementary steps of the system you try to model. And what is now very interesting, that it is possible to use these elementary steps to build such a longer run. And in this example, the light is turned on, then the light is off and on, the fan starts. It is possible to switch the light on, and the fan starts, and the fan stops. And this is a typical run of the behavior of such a system. And what is now interesting is not just to describe one particular run of the system. What you like to do is that you develop an elementary system model of that. And for that, it is just necessary to identify the labels which are labeled the same. And then you have a very simple description of this example. The elementary system description of the fan system. On the one hand, on the left-hand side, you have the cycle of the light is turned on, and the light is on. Then it is possible to switch the light off, and the behavior of this fan goes like that after some time the fan starts, and only when the light is on the fan is running. It may be after that the light is turned off again, then sometimes the fan might stops and the complete behavior. There's a question over there?
So how do you model the temporal properties of this fan? Because you mentioned the correct contact after a while. So how can you model this?
Can you repeat which temporal property you like to model?
You have the sentence after a while.
In your text, you have this this notion that if you turn on the light, after a while the fan starts.
Actually, the idea of after a while is not modeled at all. If you have a particular property in mind, then it is not very easy that here the transition fan stops can be extended by the property you like to model, and this is a prerequisite for the temporal.
Can I give you a more general answer to this? Our experience shows that you should model the functionality of the system before you start thinking about time. Okay? And here it shows you the functionality. Now if you say you wish that after you switched on the light, it takes 5 seconds or 1 minute, then the fan starts. You can put it in. You put it as an addition. So we are not against the notion of time, but if you mix the notion of time too early with the notion of functionality, then you don't understand anything. Okay? So first think about functionality, and then on top of this, put on time. Of course, with one exception, if the functionality is about clocks, and sometimes you have systems where clocks are crucial as function, and then time is a kind of data, and no longer this intuition of time. So what we all have, we simply know there is a notion of global time that goes on, and with any kind of arbitrary precision we can have it and say, aha, now this is not nonsense to put into the model. Okay? You can put it as a smart device on top. Sorry.
No problem. So the question was really regarded in the direction of temporal properties, or just some causal relations, because I think this is an interesting difference if you have some temporal properties or some causal properties. But as Wolfgang already said, the causal properties are much more interesting in doing that. So this is now an elementary system net which describes the behavior, and what of course is very interesting is how this elementary net might be enhanced with a much deeper understanding of this, because this is very simple, but this gives you a first impression what are the main concepts and the dynamic perspective. And I think now what is interesting, how the statics in this model can be brought to life, and some ideas for breathing life into logic is now the part of Wolfgang.
Thank you. So, of course, everybody expects now that we say something about data. Okay? Because we know black dots are moving around, but what is interesting is often also data. So speak about data, and instead of doing this as usually in computer science, which is, I think, debatable, at least on the modeling level, it is debatable that you have this kind of storage. you call them this is already cheating. Programming is cheating from the scratch. You call them variables, but there are no variables. That is already the point. So,
What are they? How do you call a variable?
so we start with the logic. And our idea is, well, logic exists 2,500 years. These were very smart people. So let's take what they know and let's learn from them and do it as they propose to do. And I started with Aristoteles, I started with notion of a proposition. So what is a proposition? That is something that is always true. 5 is a prime number, is a proposition, and even maybe E equals mc squared is always true. Well, since Einstein, we know this, it was true also before. It will be also true in future, I hope. And these are propositions. Proposition is always true or always wrong. Okay, and now comes the fundamental new idea. Petrus says the proposition is sometimes true and sometimes wrong. Okay? For instance, in our example, the bread is on the shelf. Well, sometimes there is a bread on the shelf and sometimes there is no bread on the shelf. But still, this is a proposition. Okay? And the idea is start this way to cover what you always do with this data stuff. But don't do too early this informatics data stuff. When you speak about objects, then do it as much as possible in terms of logic. But logicians tell us how to do this. Okay. So I wanted to make a joke because I thought that many of you think, well, to have propositions that are sometimes true and sometimes not. We have in informatics also, and it is called temporal logic, and this person there doesn't even know temporal logic. It is absolutely not temporal logic. Temporal logic is something completely different. In temporal logic, you have a transition system and you have propositions on global states, and this global state may include a lot of very complicated storage and whatever. And then you abstract from this and make a proposition of this. This is not the starting point for data. So Petrus says the proposition is a state. We start with the notion of state where there is nothing behind than just a proposition. It's true or wrong, it's true or false. And this is the starting point to conceptually model systems. Okay, and here's an example of our standard example. 8 is free, that is a proposition that is maybe initially true, but it may become wrong. And the 8 has got a pi, and when he has got a pi, and the pi is moved to the shop, then it is again free. And the question before was, we want to take logic as much as possible, and on this system level we can come back. But the boxes, so to speak, are something new. The controlled way to change the truth value of propositions. And your idea was to put this inside the transitions, which I said we will think about this. Okay, now how can we, of course this is so simple, you cannot say, squeeze everything in the world that is usually done with data into this format. That you cannot do. I show you what to do instead. And the example says when the 8 is free, he can add a pi, he can get a pi, as we said, but he also alternatively can get a cake. Okay, then we come here, and then move the cake to the shop, we go here, and the 8 is free again. And now you see the point, when you have 2 of them, you may have 3 of them, so the 8 gets bread, and the bread is moved to the shop. Okay, and if the bakery has 100 pastries, you will see how it works, and you have no fun in drawing this 100 stuff. Okay. Instead, you need something else, and I think the smarter of you may already think what direction it goes. It goes from propositional logic to first order logic. So how do we do this? Well, here is already the result. We do it. Yeah, we have a variable, X is a variable, X is not a storage, and we say if the 8 is free, then something happens and something goes to this place, and the variable varies over the set of pastries, and in the moment the pastries are these. And now we have no longer propositions, but we have a we have a predicate. The predicate is called 8 is pastry, and it includes those three propositions. So the 8 is pastry applies to bread, then we have it over here, or the 8 is pastry applies to cake, then we have it here, or we have it here. Okay? And then we glue this together to one place, and here in this place we would then write the term bread or cake or whatever we have. Okay? This is the fundamental idea. Go, as logicians tell us, from propositions to predicates. Okay, and here we have the predicate A with pastry. Now, the three transitions here, we also, of course, want to go to one transition, and that we do it this way, and therefore we need the variable x. Now we say, aha, this transition, you cannot just say, can it occur or can it not occur? This makes no sense. It occurs with respect to an instantiation of the valuation of the variable x. So if you say x is pi, then you model this transition. If you evaluate x by cake, then it is this transition, and by bread it's that transition. Okay. So in fact, this is three transitions if this is the set of pastries. It would be 100 transitions if the set of pastries is 100 pastries. Okay. Fine. And then by color you will see this. And here it of course the same story. I'm speechless. You know what he did apparently? He cheated me. I didn't see the slides until yesterday, and now I see he put something in. Okay, what can I say? Yeah. So now here we have the system model on this level as I've shown you. There's a variable y and x, and we have discussed this. And here is the variable x again, and here is the three pastries system. So here we have, so to speak, the data part, and here we have the system part. Yeah.
Just my understanding, is this model here, is this Petri-based model, is that reducible to some known, well-studied Petri model, or is it going beyond?
As far as I told you, not up so far, you can make a colored Petri-net out of this.
Okay, okay.
But wait a moment. In 2 minutes' time, you will understand that you cannot, in a more general sense, we make something much more general.
Okay, but that happens.
It's still
to happen. Okay.
Yeah. Now it is going to happen, because now I say, aha, here we have a structure with 3 bread and this function and this function. Now we have a different system with 5 bread, 5 pastries, and maybe different functions. And interesting enough, this does not change at all. Okay, here we have the symbol x, and we have description and next, but only what changed was here. And if you have 100 pastries, again the graphicals of the Petri-net up here remains, and only down here you change something. And now we remove the argument and say, what is the set of all systems that can be described by this graphical Petri-net? Okay, and then what do? You look to the logics books. And then you do what logic does. Namely, you introduce a signature. And then it becomes even simpler. A schema, so to speak. And then you say, aha, there must be a domain called pastries. We don't say which are the elements. This is a schema for infinitely many patronets. And in this sense, this is really new. This is a schema, and it tells you. Now I want to tell you about how a bakery works. Generally, how bakeries work. Okay, a bakery has a set of pastries that they produce. I don't say which concrete pastries, I only say a bakery has pastries. It has description of pastries, it has next function, etc. So on this level, it makes no sense to ask, is this transition, can this occur or can it not occur? It makes no sense, because you must first instantiate this and say, this is my concrete bakery, and you can ask, is this transition enabled in my concrete bakery? Yeah, it makes sense. But on the schematic level, it makes no sense. And you see, this is not colored nets and nothing else. This is logic. This is what I said, make logics dynamic. Okay, breathing life into logic. That is what we do. We just steal everything from logic. We didn't almost not invent anything, except the decisive point that we have transitions. So we have three systematic ways of description of a systematic changes. That's what we did. But the rest is classical first order logic. Okay? And well, this brings me already to the end of this. And now look at the time. What is the time? 8 minutes. Okay. So, originally, for some time, we thought that Frank gave us another hour. But then he has stolen us the hour.
That's what you always claim. Okay. Well,
and therefore, but in this hour, we wanted to show you that this really functions for big systems. Of course, now I cannot show you the real big system.
but you can start.
But no, well, not I don't even start. I show you what you are missing. I show you what you are missing due to this theft of fun. Okay.
That's a punishment.
So, what we wanted to show you is an internet shopping, a big internet shopping company, and this is a module. A very big module. Here is the left interface. Ordering of customers go in, accepted, delivery goes out. There is no right, there is a right interface, but it's empty. Okay? And you can imagine why this box is so big, because we put something in the box. So here we have some concrete customers. They send purchase order, they get messages, they get deliveries, and we have the business that is run. And on the other side, they send supply orders to supplier when they don't have the shoes. Maybe we order 2 pairs of shoes. One pair the business has on its files, and the other one is ordered by supplier. Then the supplier goes back to the warehouse of the business, and then there's passes go to freight forwarders, and they deliver it. Okay? And very simple, you can define this by this composition. So composition is again the same story, and you compose these things. You see, despite the fact that there is something like a cycle here, but still you can write it this way. So an interface has no order in this sense. It goes left, it goes here, you see this goes out, this goes in, but both on the right interface. Okay? You must get used to it. It is not always the case that left goes in, right goes out. It's often the case, and it's often useful to have it this way. But here it is not useful. And so the supplier gets orders and sends them the things, the goods back to the warehouse. So we had initially many examples where we had a move from left to right. But it is, yeah, you have a question.
This was exactly my question. The graph is a directed graph, then you can write it in any way. You have always arrows now. Makes a difference whether the order goes from the customer to the internet shopping or backwards. So you need
Yeah,
a directed graph, and then you can write it down as ever you want.
exactly.
Yeah. Okay.
Yeah. Okay, and now we can refine the business, and we say, aha, the business has an order management where the purchases go in and the message go out, and the order management, it looks which things are on stock and which things must be ordered by the supplier, etc. The partial goes, there are partial orders, so the management says, we know that this and that is on the warehouse, so the warehouse should make parcels, etc. So you see, we can refine this for a while, and for this, and again we have this, this composition. We say customers compose the business with fight forward suppliers, and then you can say, well, the business itself is a composition of something. You can squeeze it in, you can leave it out. It is a see how fundamentally important is the associativity. Otherwise, you could not write it this way. Okay, now fun must be, we say, so the customer we describe in detail. We describe the behavior of the customer as a patronage in very detail. We say he submits something, he has a copy of what he's ordered, and then he gets a message, and then he gets partials. And what we have also modeled in this system, if we would have shown you, if Frank would not have stolen us the hour, then we would show you how to model that you ordered, you send 3 orders, and you get 5 parcels. And well, at the end, the sum of everything in the orders corresponds to the sum of the elements in the parcels. But it's not such that every order is served by exactly 1 parcel. So all this stuff that happens in reality can be done. Okay? And then this is a typical partial order triangle. You see, that becomes quite difficult. We have this colored, I have shown you the component, the system component. This is the behavior of the system. Believe me, it is a partial order, despite the fact that you see arrows going this way. But still it's a partial order, and if you don't believe that, you can redraw this, and then come this. This is exactly the same graph as before. It's only redrawn such that you see more explicitly the partial order. And for instance, the customer occurs here and occurs here. Well, that's no surprise. The customer has ordered something, then a lot of things happen, and then the order gets something. Okay? And for instance, this long arrow says the customer has taken a copy of his orderings and okay? And again, you can give this, each of these snippets, you can give a symbol and you compose these snippets, and then you have the behavior of the system. So I insist on the value of this, because you don't always want to keep graphs in the system. You want to make it algebraically. No problem. Give a graph just a name, and then continue with this name. Okay. Yeah. Here we have, now we can do it on the schematic level. Remember, I had the schematic level also before. Now we say, this is not one concrete internet shop. This is telling us how internet shopping goes on. And here we see, now we have done it on the level of behavior, but on the schematic level of behavior. Here you can say, whenever you want your business, you should do it according to this schema. Maybe some concrete instantiations. You, for instance, you sell fish, and somebody else sells, what else can you have except shoes? Frank always wants shoes, somebody else wants fish. So these are instantiation of the same schema. Okay? Here we have an alternative, completely alternative refinement. You say, well, in such a context, you have paperwork. For instance, I order something on paper, and the administration of the system works on paper, and the paper is always in this way, and on the other side you have concrete items, shoes and fish and whatever. And we can also separate those two things. This is the paperwork component, and this is the items component. You can cut it this way out and compose those two aspects if you wish. Okay, I think that I can now come up. That was it. Now I come up with a conclusion and saying, well, classical computer science, what does it do? It has modules and composition. Well, no, this is what I said already. We want to define a composition operator this way, and we do it similarly. It is okay that we have equal interface elements and glue them, but we have not one interface but two. This is the fundamental idea. With left and right, the world looks different. The world looks perfect. The models look simple. They are much simpler than whatever you have. Yeah, we don't have one interface but adjusted by two. And this is an example, and this is how you compose, as you know. We have statics of data and items and the symbolic representation. That is what you have in classical computer science too. We do the same, but we don't have just sequences of symbols, but so to speak, the basic thing is turns over a signature, as logic tells us, things like that. Okay? So we steal from logic. Okay, and now the next thing is steps. Of course, in automata theory you have steps. So we also have steps, but not global steps, but local ones, as in Petrovic. So technically we have this composition calculus, we have predicate logic, classification, and patronage. So we combine these three things to one format. Okay? So classical computer science jumps in the right direction, I agree, but they jump too short. And, well, programming is not modeling. Programming is just about symbol crunching, whereas modeling is about the real world. Okay? With this I finish. Thank you. Yeah, aha. Now we are finished. Is there any question? Please.
Yeah. I know maybe I misunderstood, but there is a paper of Giuseppe De Giacomo and Moshe Vardi that demonstrates that the pettiness with logic, as you are doing, that you are doing with a finite domain, because you are doing with a finite domain, I assume, are equivalent to linear temporal logic with dynamic properties that are equivalent to many other formalism. So at the end, what we are doing, just because my view represents the same stuff on the modeling on Thursday. We are doing all the same way. Because when you put logic into the pattern, you are the semantics that is beyond the interpretation is easily the one of dynamic propositional logic. And it is propositional dynamic logic over finite trace, because I think that you are finding the trace at the end, your generational process. There is a paper of Giuseppe De Giacomo and Vardi of it's recent, 2 years ago, that demonstrated that are all equivalent formalism. I think that is relevant.
I know such a paper of Moshe Vardi. I'm not sure if it's this one or a similar one. The fundamental point is what means equivalence. You say there are equivalents as if it would be clear what equivalence means. And
this is my second question. Equivalence for me is that you are doing modeling, but why you are doing modeling? You are doing modeling just for verification, for example, in typical pattern nets to do dead rock avoidance, or you want to verify properties, or you are trying to automatically compute something, like they do in automatic reasoning. If we say that the two models are aimed to compute something, then Moshe did that they are equivalent in terms of semantics beyond. So the results that you can achieve from a machine in terms of computing will be the same. Then I like a lot of evidence. What I mean is that there is a bunch of recent research that are trying to show that we are all going in the same direction. When we start to put the data, and it was what I discussed as data abstraction. When you start to put the data as finite domain in order to be able to have computational power that is still computable, don't go to understandability, then we are doing similar stuff. This is my, because in the BPM community, many of these discussions are going on. Banderas has built all the idea of workflow system on the basis of patterns, and now we are trying to put the data inside as well. It's just a discussion I want to see release.
Yeah, fine, thank you. One point is the partial order aspect is ignored by Moshevadi and all these people. They make the sequences. Okay? So for the understanding of a system, I give you a notion. I say that I call a system deterministic if it has one partial ordered behavior. Okay, this notion you cannot translate. Yeah? So for the understanding of a system, we say partial order is not just fun, it is crucial, it is a central aspect. Locality, partial order, and this is not covered by those.
I really understand, because you say that you want the partial order as a building block.
The world is not jumping from state to state. Even a company is not jumping from global state to next global state.
Depends on the observability that we have. Because if the observability that we have very fine-grained, also the world is jumping from state to state. We don't see the state because we are too coarse-grained in observation. We can discuss it. Interesting discussion.
In physical terms, the world is not jumping from state to state, but this is a multi-world or something, right? Multiple terms.
But this is why the dynamic positional logic says that you can have different interpretation, and when you find a solution, you try to find the interpretation that is common to all the possible evolution. This is what from what I understand, then it's.
I'd like to add one or two comments from my perspective. The first one, of course, I'm familiar with the work which is done in the BPM community, and of course, there are so many different works, so it might be interesting to show me a concrete paper you have in mind. Actually, I think there's a lot of stuff under the umbrella of object-centric process mining, and there are many ideas for doing that. Our approach clearly differentiates from these ideas, but it would be very interesting to discuss that in more detail. Second thing you asked, what is the main motivation for modeling? And I think the main motivation for modeling is to understand the digital world. And there I come back to the beginning of our presentation. I think we need a kind of language which enables us to talk about the world we are living in, to understand the world from the perspective of the architecture, from the dynamics and statics perspective. And this is our proposal for using a language to speak together, to share our experiences, and hopefully to get a common understanding of the world. Here was a question? Oh,
regarding this variable x, so the domain here was a set of fixed symbols. Could it be a real number? So that something is transformed and it would result in an infinite number of possible states. If x is not red +3 pi, but just a real number.
The answer is very simple. Yes, of course. If you're actually logic, you do it frequently. You have the real numbers as one of the domains.
It's not a problem for the underlying logical patronage that would explore it, would just create a state if you need it.
Absolutely.
Thank you.
Of course, it's a question when you model something like that, how you would implement saying this transition fires if x has the value square root of 2. So this is difficult to implement, but as a conceptual model it is perfect.
Thank you.
So, are there more questions? No more questions? Then thanks again, and enjoy your break.